introduction. Yeah, today I'm going to talk to you about a little bit of an abstract and a theoretical work that we have been conducting in the Oxford Chemistry department in the last 3 years. How do I move forward with this? Okay. So the core question here that I'm trying to address, and I'm kind of obsessed with this, is silicon chips in our everyday computers actually does compute, and the biological cells that in our cells and in bacteria, etc., they also do compute. But these are actually physical and chemical manifestations of the world, right? And then my question is like, when and how does actually chemistry begin to compute? But on top of that, there are also other pressing, perhaps, issues in our modern computing. For example, a von Neumann architecture or like a decoupling of the memory unit where we store data and the computing unit, it's the core of the chip, is actually having a lot of issues because we need to communicate between memory and the computing. Other issue is actually that we are seeing all the time in the news, perhaps, the physical limits. It is actually impossible to go subatomic chip level, and the Moore's law is dead. And as a matter of fact, we are pretty much stuck at the 15 to 20 nanometer size of a silicon-based chip. And that also brings us to the issue of a low efficiency. And we are all using AI tools that has a lots of energy demand, and we know the AI consumes a lot of water. I just challenge you to take a look at the values, how much of water is actually used to cool off these systems actually. And another elephant in the room is the interfacing with the living matter. The silicons based computers are actually challenging to integrate with biology. But today's talk is mostly concerned about this decoupling of the memory and the computing unit, as well as addressing some of the issues with the environmental unfriendliness and high energy demands of it. And this actually is a common problem. Everybody is actually trying to look at this, and they are actually, that's why we are hearing all the time this multi-core CPUs and GPUs and etc. So what is the alternative? Some people say, including myself nowadays increasingly, is the new type of architecture. Is this brain-inspired computing in neuromorphic systems, where you basically have a goo of an interconnected network, which we call as a neural network. And in this case, it's going to be different than what actually the normal machine learning neural networks are operating. We basically put some spikes into the system. We perturb the system does something, and we get some sort of a readout at the end. So, but after this brief introduction to you here, that I would like to say, well, I'm a chemist, right? So that's why I asked, can we make these chemical systems neuromorphic? And if that is the case, can they actually complement modern electronic systems somehow? And this question has been addressed increasingly by other people as well. And recently, people have found that the chemical or enzymatic reaction networks can form neuromorphic structures. Here yet you see a just simple, out of 5 individual ingredients, a chemical networks are actually forming different types of reaction network, as well as some of the enzymatic forms of it. So what we see here is actually a fixed form of a reservoir, literally a bucket of water, and within there are multiple chemical reactions are taking place, up to dozens of, or if not hundreds. So what are the reservoirs? Let's define this first. So there are certain criteria for a physical system to be eligible as a reservoir. So we need to have a predictable output in this system through some interconnected nonlinear reaction network. We need to have some form of a time dependence in the system, where a fading memory-like behavior is manifested, in the sense that as we introduce all of these spikes in the system, as we further go down to the from a set time point, that the weight that these spikes carry at the future trajectory of the chemical reaction network is gradually decreasing. And importantly, we need to be able to link what kind of spikes actually are going to be meaning to the what kind of other output spikes at the end of the day. And this has to be done through some form of like a simple readout in the system in the form of a linear mathematical function. So, but there are some challenges, and whenever there are challenges, there are opportunities. So right now it is elusive, and it's, if not very difficult, to design these type of chemical reaction networks from the first principles. And one of the biggest issues here is actually the bulk solution or ensemble measurements actually mask the specific pathways that are important for this type of systems. And if something, if ever possible, coupling of the data storage or memory of the system to the computation is actually a very challenging task if it is ever possible. And what do I think here is actually a single individual nanopore, which is an alpha hemolysine nanopore from Staphylococcus aureus bacteria, is actually have all three properties to address all of these. So let's take a step here and then say what kind of nanoreactor is going to be done out of this individual nanopore. Let's say that we have a single cysteine residue at some position inside of this lumen of the nanopore, and then we basically apply some potential through different types of different places of the bilayer. So the current is only flowing through the nanopore. There is no other place to go. And if we basically have some sort of highly reactive chemicals, such as this selenolate or selenosulfide, that we will basically be able to form some form of like a chemical reaction in the nanopore, and that chemical reaction is going to correspond to the single molecule chemical reaction. And that is, we define it as a forward reaction. Now that we have formed an adduct here, and this adduct is going to be converted back into actually the open pore, like a non-reactive form of the nanopore. And we basically simply use some form of a reducing agent as DTT, and this is actually giving to us different types of reactivities at different positions. And in the end, if we couple all of these reactions at a very fine and balanced optimal concentrations, that we are able to actually do this, like form the adduct and then deform the adduct, or read the specific unit and erase the specific unit on pretty much until your nanopore dies off. So in order to say that we are storing data in this system, and we are doing this by this type of chemical reaction network in the most simplest way, we basically said out of 113 to 123 positions of these nanopores, whenever we see a reactive chemical residue, such as cysteine, as I said, this is going to be assigned to binary code number 1. And whenever we don't see any unreactive residue on this specific beta sheet position, that this is going to be corresponding to the binary code number 0. That can be stretched down to the different types of position, but for the sake of simplicity, I'm not really going to the details of it. Again, to recap the chemistry here, that we are basically forming an adduct with a highly reactive molecule out of selenium chemistry, and once we form all the reactants here, that we reach to a read level, and with the help of reducing agent, we are able to regenerate and repeat this system until your nanopore dies. So here is, you see an example of a single nanoreactor that is in place, that is reading the data in real time. That in the red line that you see here is a complete read, and in the gray that you see a single molecule trace of erases, and then as the chemical reactions are taking place, that you reach and sample different types of intermediate states, and we basically define this as a reread. In this overall system, out of 4 individual bits here, that through 113 to 119, we are able to achieve data reading speeds around approximately 4 bits per second. It's in its tiny step, but it's just getting started. And what is more important here is perhaps all 16 different combinations of the data stored from 1111 to 0000 are actually individually distinguishable and identifiable. That basically means that here that you see each dot represents a single specific type of nanopore trace and single idealized blockade level on the nanopore. And what we have here is none of these levels are actually exactly overlapping with themselves, meaning that all of these tapes are basically differentiable from each other. This is a chemical data storage in the hard-coded form. And what about actually converting this type of nanoreactors as chemical reservoirs, as I already given you the introduction? So if you were to increase the amount of chemicals here, that you're inevitably going to increase the amount of potential chemical reactions. So for the sake of simplicity here, that I devise a 6-member chemical reaction network out of 3 different diselenides and the 2 different cysteine positions at 113 and 117, and a single reducing agent. What happens in between is all of these possibilities, and this is not actually down to the real case scenario here. This is basically some form of abstraction of what all the possible chemical reactions are taking place during the reading of a 1010 memory tape. And what you have here is a fixed reservoir, meaning that in regular machine learning systems, what you do is you train your neural network. Your neural network evolves as you're addressing your question. But in reservoir computing, your reservoir is a fixed, and what you're doing is you are training the readout, and you're learning through the readout level, meaning that everything that comes out of as a useful computation is actually inevitably a product of the reservoir, because reservoir contains highly rich dynamics here. And what we did here is in the first example of like whether this reservoir is doing the job that we are actually asking. What we did here is actually look at all these like potential different nanopore data that we stored. This is like from 1000 to 1111, and classify all of these, whether you will be able to understand what you actually yourself generated through your own chemical dynamics. And indeed, to our pleasure, that we would be able to distinguish at more than 90% accuracy of all these 15 different memory tapes. There are some hiccups because of the structural similarities of these data reading processes, but long story short, the system is, even at such a short observation window, even less than of a 5 second, you will be able to distinguish fairly similar types of memory tapes in the system. And you can even actually go down to the level that the human eye basically cannot really distinguish at a specific snapshot. And to confirm that whether this system is actually really learning something, that we done negative control experiments where we are actually blocking or diminishing the correlation between the label of the specific memory tape or the types of other features that we are actually looking at. For example, what kind of blockade level, etc., is taking place. And rest assured, I can tell you the system really is not learning anything that is trivial. It's really going through its own chemical dynamics. So that being said, we also have other different criteria to meet to define the system as a functioning proper reservoir. Again, I go back to the 6-component chemical reaction network here, and here that you see all the possible nanopore adducts, that all 15 different levels out of this chemical reaction network that we can reliably distinguish by just looking at the chemical traces. And what I say here is, let's group these pretty arbitrarily, group A and group B, and then try to understand whether group A that we are looking at group A or group B. And here that is an example of what kind of single molecule or single channel recording traces that we are seeing here. Just by looking at human eye, this basically takes pretty much forever to actually even understand what it is to individually assign all of these levels. It takes some time, weeks or a month or something, but you'll be able to get through the bottom of it. So the question that we ask here is another computational question is, look at some chemical reaction network trajectory and then tell us whether you will be able to predict what the future trajectory is going to be. We have picked a fairly difficult question for that rather than asking a simple question such as, just tell me exactly what's going to happen. That is pretty much actually impossible to guess because that you're going through a system at the end of the day is a stochastic, so you cannot really actually predict very high efficiency. So then we define the system as, let's look at some observation window here, and vary the observation window. We obtain some information and some statistics out of that. And then let's guess whether the group A in the previous slide is going to happen first or group B is going to happen first. This is basically, at the end of the day, it's a similar task, and it's even more difficult task to say that the current or observation trajectory is going to correlate to the future trajectory. And what we have seen here is when we just change the observation window level, that we basically see a peak around like 4 seconds, and when we change the prediction horizon window, that we are actually seeing a consistent 3-second peak around here, meaning that the memory in the system, that is fading memory, is actually really the property of the reservoir, meaning that our chemical computer is functional as it is supposed to happen. And another evidence through that is this chemical reaction network inside the nanopore is actually tunable. When you change different concentrations of chemicals, different types of network complexity, or using different type of cysteines or different type of memory tapes, you are always getting some sort of a consistent and a different readout at the end of the day. So to summarize, and in the next couple of slides to give you a little bit of an outlook here, the same single molecule dynamics, both participating in the data storage, physical storage, and the computation of this, and that means you are having a unified physical manifestation of these things as a single unit. It's not inherently separate, it's actually the same thing. So that actually also reports us this system, since it operates at the single molecule level or few molecule level, is actually the smallest physical reservoir reported to date. And we believe that it's generalizable to the other types of networks as long as that you have reversible transitions, and it actually also satisfies all the characteristics of the reservoir as I mentioned. So now that we have a reservoir or computer and the memory coupling here, what we can do with this system is actually parallel computing, such as a mini-ion, a nanopore computing system. We can actually use hundreds, if not thousands, of individual nanopores, and we can actually reach the computing capacity that is beyond any other chemical system that is actually able to achieve. That being said, with using droplet interface bilayers or some other vesicle-based smart materials, we can actually interface with the chemical computing systems to the actual biological matter in a much more smooth way. Another point is the high efficiency or ultra-low energy consumption of this system. To give you some interesting insights here, a single read cycle of this system is just below 100-fold of the absolute thermodynamic limit of this system. Is just only shy of 10 to the minus 19 joule per read cycle or per compute operation that is this system is actually dissipating as an energy. I think this is an important feat, and we should be able to keep that in mind. And the last thing is I would like to mention is the next step is here is like a really difficult mathematical function is supposed to be given in this chemical computer, and we should be able to find a solution to it, and we are basically working on it. And with that, I conclude here. After seeing all this evidence, in my opinion, I start to think that information storage and information processing are perhaps an inherent capabilities of chemical matter. So far, we have seen these silicon chips are engineered systems, and we always have the notion of, well, these are different from our chemistry or different from actually what the physics. We engineered this. But perhaps with this platform technology, we can ask, how can information storage and processing can emerge, propagate or scale, or even further going into the different types of further philosophical things, that how can chemistry adapt and evolve. And with that, I would like to thank all of you and my professor P.I. Hagen-Bailey and student Elif and Disha. Thank you very much.